Chapter 51, Part 2. So the last chapter I introduced you to ecology, and we looked at different levels of organisms, populations, communities, ecosystems, biosphere. And for Part 2, we're going to focus on that last one. We're going to focus on the biosphere. So the biosphere is basically everywhere that living organisms reside on Earth. So it includes water and land and air. And so we're going to talk about the interaction of water and air with the sun and greenhouse gases. So in other words, we're focusing on climate change. All right, and so I stole this from the YouTube video you can see in the link. And this gives a pretty good overview of where we're going. And I highly recommend that you watch the video here that I've linked to. He does a better job than me, if we're being honest. But we're going to talk about global climate change. So basically just changes to the climate on a global scale over time. And you can see there's two main driving factors. There's solar radiation, so the sunlight that Earth absorbs. And then the greenhouse effect, which we'll talk about shortly, basically a blanketing effect that traps heat on Earth. The greenhouse effect is generated by greenhouse gases, and you can see some of them listed here. The big one is CO2. We'll talk about why that is in a little bit. Where do these greenhouse gases come from? They have different sources. Some of them are natural. Some of them are anthropogenic. That just means they're produced by humans. And so with anthropogenic greenhouse gases, they're controlled by government regulations. They're controlled by treaties that various nations enter into. And basically the amount of anthropogenically produced greenhouse gases changes over time based on primarily their use of fossil fuels. All right, global climate change is going to have various impacts. Some of the impacts will be on the environment, and some of the impacts will be on humans. All right, so we'll touch base on most of these throughout this lecture. Okay, so first up, let's talk about the greenhouse effect. We've already talked about solar radiation a little bit in the last video, so I hope you understand the ways that sunlight hits the Earth as the Earth orbits around the sun on its annual cycle, and how the tilt of the Earth causes different amounts of solar radiation to have various impacts at different latitudes. But let's talk about the greenhouse effect. So what is the greenhouse effect? Well, if you've ever walked into a greenhouse, you know that it's pretty warm in there. Why is that? Well, it's because the sunlight passes through the panes of glass, and then it radiates heat, and then the panes of glass that make up the greenhouse trap the heat. So a greenhouse traps the heat and maintains a warmer temperature than the outside. Similarly, the Earth has a greenhouse effect. So the atmosphere consists of various gases, and these gases allow some solar radiation to pass through, right? Some of it is going to hit the Earth or hit the atmosphere and bounce back into space, but some of it is going to hit the Earth. When the solar radiation hits the Earth, it's absorbed, and some of this energy gets given off as long wave radiation, which we'll just call heat, and that heat radiates back out into the atmosphere. And some of it will escape into space, but then some of it gets trapped by the atmosphere and therefore warms the Earth. So in other words, the greenhouse effect is just the warming of the Earth due to the presence of greenhouse gases in the atmosphere. Here's another picture of the same thing. So the solar radiation from the sun comes in, hits the Earth. The heat is radiated as long wave radiation. And then again, this layer of greenhouse gases traps some of it, acts like a blanket and traps some of it, and helps keep the temperature of the Earth warm. So what happens if you change the amount of greenhouse gases? If you change the amount of greenhouse gases in a way that increases them, then it has the same effect as you adding more blankets to your bed at night. You're going to be warmer. And so more greenhouse gases in the atmosphere trap more of the heat that's radiated from the Earth and lead to warmer temperatures. So what are greenhouse gases? Well, there are several. There's water vapor, carbon dioxide, methane, ozone, chlorofluorocarbons, hydrofluorocarbons. And we're going to pass over most of those and focus on the main one. So carbon dioxide is going to be the main greenhouse gas that we're going to focus on because it's one of the major players. It's the major player in global climate change. But the point is there are multiple greenhouse gases that exist in the atmosphere and provide or contribute to the warming of the earth. And they are produced by humans through various activities that we do. So transportation is the source of about 28% of the anthropogenically produced greenhouse gases in the atmosphere. And so how does transportation produce greenhouse gases? Well, primarily through combustion of fossil fuels like diesel and gasoline and so on. Industry produces greenhouse gases like carbon dioxide. How do they do that? Well, they use electricity. Where do they get the electricity from? A lot of the electricity is produced by burning fossil fuels like coal and natural gas and oil. So anyway, oops, you can see that over here in electricity. But anyway, you get the point. Anytime we want a source of energy, we need an energy source. And when we're using energy sources that are based on fossil fuels, the combustion of fossil fuels creates greenhouse gases. I mentioned that there are anthropogenic greenhouse gases, ones that are produced by human activity, but then there are also naturally produced ones. So in this graphic, you can see on the left that various natural processes produce greenhouse gases. In other words, greenhouse gases are totally natural in the atmosphere. And this is good because this, again, keeps temperatures at Earth warm enough to sustain life. So what types of natural processes produce natural gases? Greenhouse gases, I'm sorry. Decomposition does. Volcanoes can produce a lot of CO2. Forest fires combust wood material, plant matter, and that releases CO2 and other greenhouse gases. But you can see that in recent times, human activities have vastly or have outpaced natural sources of greenhouse gases. So human activities produce more greenhouse gases collectively than all of the natural processes combined. All right, and so how quickly are these concentrations changing? I mentioned that if they increase, it's going to warm the earth. Well, what's going on with them? This is nitrous oxide. So this is a greenhouse gas. I don't know if I mentioned that one earlier when I read off my list, but anyway, you can see here that it's been increasing over its concentration in the atmosphere has been increasing over the last 150 years, especially in the last 50 years. Right? And so it's gone from 270 parts per billion to around 325 parts per billion currently. How do we know about these increases in greenhouse gases? Well, in the last 50 years especially, we've been sampling them directly. So in other words, we're sampling the gases of the atmosphere and analyzing them and seeing what gases make up the atmosphere. So a famous example of that is this data. This is from the Mauna Loa Observatory in Hawaii, and a scientist named Dr. Keeling, for about 50 years, had a little setup where he would sample the atmosphere in Hawaii, in the middle of nowhere in the Pacific Ocean, and he would write down his records. And so this continuous collection of atmospheric gases has revealed that carbon dioxide concentrations have been going up. So when he began his experiments in the late 50s, the CO2 concentration was less than 320 parts per billion. I'm sorry, parts per million. And then you can see now it's around 400 and it's almost 420 parts per million. So a pretty significant increase. Right? This is another representation of the same thing. This one goes back a little bit further. So here are estimations of CO2 concentrations in the atmosphere over time, and you can see that they were more or less equal, more or less balanced, more or less, what's the word? Help me out, guys. They didn't change a whole lot. And again, in the last 100 years, you can see that the CO2 populations have risen exponentially. All right, and to get a feel for that, you can go to this video, which I'm not going to play, but you can go to the PowerPoint and click the link and watch it. And this is a video produced by NASA where basically they just track CO2 through the course of a year. And so this red color is representing carbon dioxide in the atmosphere. So at this point in time, there's a ton of it in the northern hemisphere, and I believe this was from the winter. I forget which month I took this screenshot. But you can see that the CO2 is produced by burning fossil fuels primarily. It goes in the atmosphere. It hits those winds that we were talking about, gets moved around, and basically spreads out throughout the entire atmosphere over time. So through the course of a year, CO2 levels are rising and falling, but overall the trend has been that the concentrations have been increasing. Where is the CO2 coming from? So I've mentioned fossil fuels, so you can see here that this is the amount of CO2 emitted by combusting various fuels. So initially, in the Industrial Revolution, coal was the primary source for heating and cooking as the Industrial Revolution kicked off and for producing steam and eventually electricity. And then oil came on the scene in the 40s and 50s and continues to this day. Natural gas has become more important over time. And then there's some other phenomena we won't talk about here. But again, coal, oil, and natural gas, primary sources of CO2. All right, and notice the scale here. This is billions of tons. So a ton is 1,000 kilograms, or about 2,200 pounds. So if we're talking 35 billion tons of CO2 that's produced, then you have to multiply that by 2,200 to convert to pounds. So what is that? Like 70, my math is terrible. Somewhere between 75 and 80 trillion tons of CO2. So we're talking huge amounts. So you can see that not all nations produce CO2 at the same rate. So the US is a leading producer or a leading emitter of CO2. Why is that? Because we're very industrious. We make a lot of things. We drive our cars everywhere. So we combust a lot of fuel. And also we have a lot of money to afford manufacturing and to afford fuel to burn for heating our homes and so on. So you can see that richer nations, or industrialized nations at least, produce more CO2 than your non-industrialized nations. So if you break it down per capita, places like the United States, again, lead the world in terms of CO2 emissions per capita. All right, and so with global climate change, scientists are trying to figure out, okay, look, we're burning a ton of fossil fuels. We're increasing the amount of greenhouse gases in the atmosphere. What is that going to do? What has that been doing to the atmosphere over the last century, and what's it going to do to the climate over the next century and beyond? And so you can see that scientists try to model what the future looks like. So you can see here, this is emissions, so CO2 emissions. This is what we've observed. That goes back to some of the graphs that I showed you in the last couple minutes. And then they project how much CO2 is going to be emitted over the next century. All right, and then they use those emissions to calculate the effects of how that's going to affect the greenhouse gases, concentrations, and how that's going to help trap heat and warm the climate. And so basically there are different models that project, that basically look at all the ways that various factors in the climate or in the atmosphere or in Earth's surface interact, and that they try to predict how climate change will progress in the future. All right, and so there are different models, and so here we are currently. And if we didn't do anything, so if we had no climate policies, then the models predict that in the next century, we're going to see an increase of the average temperature on Earth by somewhere between 4.1 and 4.8 degrees Celsius. And so that translates to about a 4-degree change in centigrade results in about a 7-degree change Fahrenheit. So that might not sound like a lot, but that's pretty significant. That's a lot of warming. Okay, but we have policies. We have policies that are trying to reduce greenhouse gas emissions, so government regulations, treaties, pledges, so on and so forth. So with current policies, we can see we can reduce the warming by about a degree centigrade. If all the nations that have pledged to cut their CO2 emissions do so, then we can see that it will maybe only increase temperature by about 3 degrees. Right, so the point is there's models, and again, we don't know how much emissions are going to be in the future, but there are models that are trying to take into account kind of worst case scenario versus best case scenario. All right, so let's look at global climate change in a little bit more detail. So first of all, global climate change is happening. If you look at the 10 hottest years on record, so basically just taking global temperatures and averaging them, you can see that the last 5 years have been the hottest 5 years. Right? So 2016 is the hottest on record, followed by last year, 2019, and then 2015, 2017, 2018, 2014, 2010, 2013, way back in 2005 and 2009. So the hottest years on record have been in the last 15 years, with the hottest 5 being the last 5. And if we take a historical look, okay, so it's been hot in the last 15 years, but how do we know this isn't natural? So these are temperature anomalies going back to the 70s. So in other words, in the 70s and 80s, you can see there was this cycling where the temperature was a little bit cooler, and then there was a short period of time where it was warmer compared to historical averages, and it was cooler. So there's kind of a cool period in the 70s and 80s. And then as we get into the 90s, it starts warming up. And what you see is as we get into the 2000s, this upper part of the graph, the warm years, start taking over. So there's fewer cold periods, and you can see that there are not only more warm periods, but the warm periods become more and more dramatic. Right? And so here's some of that same data just expressed in a different way. And you can see that the baseline temperature, again, we kind of had some colder temperatures at the end of the 19th century, but in the last 20 to 30 years, global temperatures have been rising at a rate that's faster than what we would expect from natural climate change. Where's all the heat going? Well, a lot of that heat is being absorbed by the ocean. So some of the heat is being transferred to land and to ice caps into the atmosphere, but that's really small compared to the ocean. So overall, the ocean is heating up at a faster rate than the land or the atmosphere. So a lot of uh, this heat increase, temperature increase, again, is primarily showing up in the oceans. So what's the big deal if oceans are warming up? Well, that's going to change pH for reasons that I won't get into here, but slightly warmer ocean temperatures are going to affect evaporation rates and they're going to move warm water around and therefore heat up more of the earth. And so the heat doesn't just stay in the ocean. It's gonna affect land and atmospheric temperatures as well. So here are land and ocean temperature percentiles. This is 2018 data. So a couple things you can see that, and you'll see this pattern throughout this lecture, that the temperature rise, it's not even. So some places are going to see record warm temperatures, and other places might actually get colder. But overall, you can see there's more red than blue. So overall, the average is going up, but some places are going to warm faster than other places, and places might actually cool. So it's difficult because we're talking about global scales here, and so the globe, the Earth as a planet, isn't going to heat up everywhere at the same rate because of wind patterns and differences in solar radiation and all that stuff. But again, the overall trend is warming. As the oceans warm, they will expand. And so the expansion of the ocean will raise sea levels as ice caps or as snow or um, glaciers melt. That water runs off, that liquid water runs off into the oceans and raises sea levels. So you can see that how over the last, 130 years or so, sea levels have been rising. So this is in millimeters. So it's gone up maybe what, 100 millimeters in the last century or so. And so that might not sound like a lot, but if you live near the coast, the sea level just coming up a few millimeters is going to be a big deal. Scientists estimate that for every 1 degree Celsius increase in temperature, that will translate to an increase of about 4 feet in sea level. So if these projections of a warming climate come to fruition, we can expect to see greater volumes of seawater and therefore higher sea levels. And so, again, places like Florida or cities along the coast like New York are going to run the risk of being inundated with seawater. So, again, here's the predictions. Uh, Looking out to about a half century from now. So this is 2070 to 2100. So you can see again, overall, we're going to see increases in temperature. And I mentioned the average worst case scenario is about 4 degrees Celsius. But and because that's an average, some places are going to warm less, whereas other areas are going to warm to a greater extent. So the greatest warming is predicted to be in the northern hemisphere at high latitudes. So the North Pole is expected to get hit harder than Antarctica. One reason for this is when you saw that video or that screenshot of the NASA video that was showing CO2 concentrations as they were emitted from fossil fuel combustion. Most people and most industries and most fossil fuel combustion is happening in the northern hemisphere. So that means that there's going to be more heat trapped in the northern hemisphere, which is why it's more pronounced at high latitudes. All right, what are the impacts of all of this warming and increases in sea level? So some of the main effects are going to be from the distributions of plants and animals, timing of events, community makeup, and maybe extinctions along with human impacts. So we'll talk about all those. So in this picture from your textbook, um, you can see the distributions of different species of plants that make up various tree communities, forest communities. So here we are in East Tennessee. So we're in an oak hickory forest. That's the dominant forest type that we're interacting with. And you can see up in New England, it's mostly maple, beeches, and birches, and so on. And up here in Minnesota, it's aspen, birch. Well, as temperatures increase and as it warms, then these species that are adapted to warm temperatures can move south. Can move north, and these species that like colder temperatures will be forced to move north as well. So what you see is that the models predict that these southern species are going to move northwards and these northern species are going to move up into Canada. So we expect to see um, forests change just in terms of the trees that can thrive under those climatic conditions. This is showing projected precipitation changes by seasons. Right? And so again, this is just a model, but it's just showing how scientists are trying to predict how these warming temperatures will affect precipitation. And you can see that this model is expecting higher precipitation in the higher latitudes and less precipitation, so more dry air, much warmer temperatures in the lower latitudes. So more rain up here, less rain down here. So obviously that's going to have impacts on the types of plants that can grow in these regions and therefore the types of animals that can live in those forests and those ecosystems. This is going to affect animals, especially areas where there's high biodiversity. So, so animals, species like leopards that live in Northeast Asia, that like colder temperatures, might have to migrate northwards, just like the trees did in the last projection. These animals might have to follow the new distribution of the trees and move northwards. So anyway, the take-home message here is it doesn't just affect plants. Climate change is going to affect animals because it's affecting the temperature, it's affecting precipitation, it's affecting the plants that they're eating, and so that can lead to um, habitat loss. It can lead to um, even extinction events to some of these more threatened species. Here's another example of how warming might affect fisheries. So as the oceans warm, it's predicted that it's going to affect species that prefer cold water temperatures. So you can see in subtropic and temperate oceans in the 1970s, it was, we had lots of fish that thrived in cold, cold water. And then as the oceans warmed in the last 30 years, we see a shift with more tropical and subtropical or warm water fish. And in the future, we can see the temperate cool water fish getting squeezed out. Right? In the tropics, we can see that over time, as the oceans continue to warm, it might put so much pressure on fish populations that we see a crash and we just have smaller fish populations and less biodiversity. Humans are going to be impacted by climate change, but not to the same degree. So depending on where you live on Earth, you're going to be impacted in different ways. And so populations that are in places that are going to be affected by sea level rise will be affected more drastically. So this would include places that have low sea level or places that can be inundated by the oceans. Other places won't be as affected, like Canada. So again, we're going to see effects throughout the globe, but not all populations are going to be impacted to the same degree. What about human impacts? So this is just summarizing some of the impacts of climate change on human health. And so the rising temperatures and increasing CO2 levels can change like where mosquitoes live. So in other words, mosquitoes might spread northwards as temperatures warm. They might be able to spread to higher latitudes. So these insects can spread diseases like malaria, for example, or um, dengue fever or West Nile, and so they might move northwards, say moving from Central America into North America. The inundation of land with seawater will impact freshwater supplies. It will affect water quality. So anyway, severe weather. So maybe we're going to have more storms or more unpredictable storms. Um, so anyway, the point is, it's gonna cause a lot of changes that humans are going to have to adapt to. All right, and as I've been talking, maybe you've been saying, "Well, I'm not. I don't think I really buy into global climate change." So I thought I would talk about some common um, arguments against global climate change. So this is a good website, skepticalscience.com. You can click this link in the PowerPoint, and you can find where they cover a lot of arguments in addition to the ones that we're about to talk about. All right, so first, um, one of the questions that comes up a lot is how can there be warming when it's cold outside? So in other words, if we have these cold snaps or we have a snow event in September out in Colorado or something, then is that evidence against global climate change? So here's an example of a tweet, and I deleted who tweeted this um, because that's not the point. This is just a good representation of this attitude. So this tweet is saying, in the Midwest, this is in January of 2019, in the Midwest, there's wind chill temperatures that are minus 60. It's really cold. So where are you, global warming? So it's basically saying, how can there be global warming when it's really cold in the Midwest in January? And the reason for this is the jet stream. We talked about the jet stream in the last lecture. So I mentioned how the jet stream is this cold polar air that's kind of circling around the globe, and sometimes it becomes unstable and this cold air dips down. And so what was going on in January of 2019 was there was a dip like this where this cold polar air moved south and was covering much of the Midwest. And so that's an example of just how global climate change doesn't necessarily mean that we won't have cold periods or that it won't be cold in the Midwest. That's just the consequence of a dynamic climate. Another question is, how can there be warming when Antarctica is gaining ice? So in other words, if there's global climate change and the world is warming, then we expect the ice in Antarctica to be melting. Well, what's going on with Antarctica? So this is showing the North Pole in March and September, and then Antarctica in March and September. So you can see that there are natural fluctuations in these ice sheets at the poles. So in South America, or the southern hemisphere, for example, you can see that the sea ice levels shrink when it's warmer and expand when it's colder. So remember that this is the southern hemisphere, so this is the beginning of winter and this is the end of winter. So you can see that Antarctica naturally has fluctuations, and the same is true for the North Pole. So this is coming out of winter, so we got lots of sea ice, and then at the end of summer you can see the sea ice has shrunk. So that's natural. What's going on in places like Greenland? No, um, this is Greenland, and this is showing Antarctica. So this is showing, so Greenland is mostly covered in ice. Right? It's really high latitude, really cold, and this is in August of 2019. And so they're looking at how ice on Greenland has changed since the previous year. So you can see on the western side, you get a reduction in ice. So this ice is melting. And you do get some gain in ice on this side. So that's just differences in local climate. But overall, the amount of ice that's being lost is greater than the amount of ice that's being gained. Similarly, in Antarctica, you can see that East Antarctica, the ice sheet is remaining more or less constant, so about the same size from year to year. But in West Antarctica, you can see that the overall amount of ice is being reduced. So again, some places are staying the same, where other places it's being reduced, and the overall rate is that these places, Greenland and Antarctica, etc., are losing ice at a rate faster than they're gaining it. And someone might say, well, scientists predicted cooling in the 1970s. How do we know that, they were wrong then? Maybe they're wrong now about predicting warming. So let's go back to the 70s. So this is a survey of scientific studies on cooling. And you can see that about 10% of the papers that they surveyed predicted cooling. However, about 62% predicted warming. So you got to be careful, because someone might, on social media, they might say global warming is a joke, global climate change isn't happening, and they might link to an article that was written in the 70s saying it's going to be cold in the future. Well, those articles existed, but even back in the 70s, they were a minority. Right? The bulk of the scientific community has been predicting warming because of this greenhouse effect and increasing CO2 emissions that we talked about earlier. Right? And so now, if we were to look at current papers, you would see that the pie would be almost all red. In other words, there's more and more consensus in the scientific community that global climate change is happening and is man-caused. Right? And so to that end, let's look at the argument there's no consensus among scientists. So like I was just saying, if you look at, if you survey scientists, and so some scientists have lots of expertise in climate science, others have lower expertise. And so the more expertise they have in climate science, then the higher the consensus. So in other words, the more you learn about how the climate works and about these greenhouse gases and emissions, there's more and more consensus in the scientific community that global climate change is happening and that it's caused by human activity. All right, so that's, oh, whoops. And then last point, I always do that, don't I? I always forget there's one more slide. And so the public, because of the influence of media and other reasons, the public perception of the consensus, if you survey just people on the street, then they say the person on the street is most likely to say, well, I think somewhere around 30 to 50% of scientists agree that global warming is caused by humans. So the reality is it's closer to 97 or 98%, right? And so the perception of what the scientific community thinks is shifted to the left. And so people basically don't realize how much consensus there is in science in support of global climate change being caused by human activity. All right, so that's a crash course in global climate change. In the last lecture video from this chapter, we'll talk about biomes. See you next time.